And you can see really what you can see clearly what's going on, that the first one has to be, you start with this, it's just this copy of R, that's your first step in the filtration. So we have to then sitting inside R with the zero differential. In the second step you cut out at this level, this is sitting inside the differential module corresponding to this truncation, and of course finally you have the whole thing, the whole differential module. Maybe I call it S. S is a bad choice, sitting inside this copier. And it's clear that the filtrations have the subquotients are projective modules. In the first step you just have R. In the second step, if you filter this by R, you're left with two copies of R. And if you filter the whole thing by this submodule, you're left with R itself. Yeah. So you know this condition that it has a zero differential, it's tantamount to saying that the differential on the module takes Fn and puts it in Fn minus 1. But what can happen is that it can also go much further down in the filtration, as you see in this example. The differential takes R and it lands down here. And that's what distinguishes differential modules from complexes. Okay? So at this point, maybe I may come back to this later, but I might have, I might have wanted to discuss what the existence of a flag means on a differential module, on a free module, but let me reserve that comment for later. Let me make the following comments that, first of all, if a differential module has a flag, it has to be projective to begin with. That's clear. Projective as an R module. But the converse is not true. So even if the underlying module is projective, it need not have a flag. So if you look at, for example, just look at this ring and the differential module given by R itself and multiplication by R. Yeah? So it's the ring X. Yeah? It's a ring where the endomorphism is just multiplication by X. And this doesn't have a flag because there's no way of filtering it in such a, because it's indecomposable, for example. Okay? And the second remark I want to make is that the reason, so maybe I make this remark here, is that differential modules with flags, so F, the reason this property is interesting is that this means that it's F is a cofibrant object in some model structure on the category of differential modules. So it has a lifting property. Has a lifting property for projective objects. So as I said, this is sort of developed further in this joint work with Christians and Piepmeier, etc. Yeah, there's a model structure on the category of differential modules where, okay, not these, but direct summands of these flags form the cofibrant objects. So that's why these are important. These are analogs of complexes of projectives in the category of complexes. Okay. Now, as you can see from this example here, having the existence of a flag is just saying, for example, that it's like the complex of projectives, whereas what we are interested in is the analog of perfect complexes. So to get there, make the following definition. And this definition is exactly analogous to what I discussed yesterday concerning class. So F, a differential module, then the class of F is so the least integer C such that F has a filtration, a C-step filtration, a C-step flag. With f of C is equal to F. So it has a flag of length C. Yeah? So it's the least C for which it has a flag of length C. So if no such flag exists, then the class is infinite. Yeah. So this is the classes, the differential modules of finite class are the analogues of the perfect complexes. So for example, if you start with a perfect complex itself, so if P is a perfect complex, then in the class of P, the corresponding differential module. So we know that such a perfect complex has a flag. We just discussed it. It has a flag of length, I guess it is B minus A. Yeah, I just erased it. It was right here on the board. Given a complex of perfect projective modules, I described the filtration of the corresponding differential module, a flag on the corresponding differential module, and from there you can see immediately that the class of the corresponding differential module is no more than B minus A. Yeah? On the other hand, if you look at here, this example here, the class of this differential module is, maybe I should really call it something. Let me call it SC. Oh, no. Okay, let me call this differential module S. So the class of this differential module, we had the filtration here. It's the zero step is this, the first and the second. So this is less than or equal to 2. Yeah. So let me remind you that it had a filtration. And S. So this is the zero step of the filtration, the first step, and the second step is everything. So the class of this one is at most 2. You'll see soon that the class is in fact equal to 2, and that's really one of the issues, one of the things I want to discuss next. How do you get estimates on the class of differential modules?